Welcome back. In this video, we're going to continue the application of statistical thermodynamics to quantum mechanical systems. Now, when we first learned about statistical mechanics, it was in the context of classical mechanics. And in that case, we had to discretize phase space in order to count microstates. Now, it turns out in quantum mechanics that when you have a system that's bound by some potential energy surface, that the position, momentum, energies all become naturally quantized or discretized. So we really can take those equations that we developed in that classical context and use them without much modification in a quantum mechanical application. So let's take a look. So if I want to count microstates in quantum mechanics, let's start with, say, a microcanonical ensemble where I have, say, 10 to the 23rd particles with a given energy E and some fixed volume V. So to count the number of microstates that would be consistent with this macro state, I'm going to set up Schrodinger's wave equation with my 10 to the 23rd particles, and I'm going to solve the wave equation. I'm going to find all the energy eigenstates, and I'm going to count the energy eigenstates that have an energy E that's consistent with my macro state, my microcanonical ensemble. And that's the approach we're going to take. Now, of course, practically speaking, you're not going to be able to do that, but conceptually, this is correct, and we're going to be able to use this approach for smaller systems when we get to the molecular microcanonical ensembles. So when we take this picture here, we know that we counted our number of microstates with this approach. We can also similarly assume that the probability of each microstate is just 1 over the number of total microstates. So that is the same as before. And also, similarly, we can calculate any thermodynamic property, the ensemble average of any thermodynamic property, by calculating taking the operator for that property, calculating its expectation value for a given microstate, weighting that by the probability and summing that up over all the microstates to get the ensemble average for the expectation value here. Okay, so it's pretty much the same approach. It's just we're simply counting our microstates by looking at the eigenstates that have the energy of a given macrostate. Okay. When we move on from the microcanonical ensemble to the canonical ensemble, we can get a partition function with pretty much no change. So we have exactly the same equations, but we're going to take the counting that we did here, and we're just going to use that microcanonical partition function in our canonical partition function, and everything remains the same. And when we get to non-interacting molecules, then we can now then write the canonical partition function in terms of a molecular canonical partition function. And here's where it starts to become practical, because that is just the sum of our microstates over the discrete energy levels in mu space. So in other words, we only need to solve Schrodinger's wave equation for the smaller individual molecules that are all not interacting. So we have one molecule, it's not interacting with other molecules, and then we can solve that problem, and we can get properties like the thermodynamic properties of gases and other non-interacting molecules in that sort of ideal gas approximation. So that's the approach that we're going to take in this chapter. So we can calculate these energy levels, we can get the degeneracies, we can calculate the molecular canonical partition function. From there, we get back to the canonical partition function, and then we can calculate properties. So for example, if I have a gas of n identical molecules, each having x atoms, then I know the energy can be approximated as just a sum of the individual types of motion. So the translational motion, the vibrational, rotational, electronic, and nuclear motion will include. And that means that the molecular partition function can be similarly approximated as a product of the molecular partition function for just the translational motion, the rotation, vibration, electronic, and nuclear motion then. When we take that to the canonical partition function, we can then write the same product. So we have the product of translation, rotation, vibration, and the nuclear motion, and then taking the logarithm of this, we just get individual contributions in a sum, which means that if we calculate any thermodynamic property from the log of our canonical partition function, then it's just going to be a sum of contributions from translation, rotation, vibration, electronic, and nuclear contributions. So we can look at each of these contributions separately, and then when we're done, we can bring them all together to calculate the total thermodynamic property for that particular system, okay? So let's just start with the nuclear partition function, just to show you how we would go about for one of these, and then we'll continue with the rest of them. But this one is probably the easiest because we're just going to assume that all the nuclei are in their ground state. There's no excited nuclear states. In other words, we're not dealing with nuclear reactions or radioactive systems. We're looking at systems where all the nuclei are stable and they remain in their ground state. In that case, then the ground state has a degeneracy of 2I plus 1, where I is the nuclear spin. And we can also redefine the ground state energy as 0, even though there is some energy associated with the ground state, but that's going to remain constant in all of our systems. So we can just redefine that as 0, and it won't affect any of our properties except for the entropy. And if we do that, then our partition function just simply becomes the product of all of these degeneracies for all the nuclei that are in our molecule. And that's pretty much it. Most of the time, this is just left out of the calculation because it doesn't really contribute, but we've learned before that the symmetries of the nuclear ground state are important when you're trying to build a molecule wave function that is symmetric or anti-symmetric with respect to nuclear exchange. So we may have to bring it back if we're dealing with some of those particular situations, which we will later in these video lectures. So that's it for this. I'm going to go now and I'm going to write a video for each one of these different contributions, and we'll see how we have to sort of develop the approach for the different types of motions.